I'm Mike Campin, VP Product and Engineering at Jamf. Today, I'm going to talk you through the architecture of the new Jamf Security Cloud. Here's the agenda for today's talk. I'm going to start by giving a high-level overview of the platform architecture. Then we're going to look at a selection of product use cases to help bring that architecture to life. Then, once we're equipped with a good grasp of the basics, we're going to take a more detailed look at some of the specific areas of the architecture, including our global edge, the clients, and finally our microservice core. Along the way, I'm going to call out some of the key strengths of the platform and, as a result, why it comes together to provide such a great end-user experience. Now, you may well have seen this diagram before. It shows the three main products delivered from the Jamf Security Cloud. Jamf Threat Defense protects mobile workers from a broad spectrum of threats, including zero-day phishing. Jamf Zero-Day Policy allows customers to apply endpoint compliance and usage policies. And then finally, Jamf Private Access, our ZTNA product, provides safe, secure access to enterprise applications. Now, whilst each of these products serve different business needs, from a technical perspective, they all center on or around the network. And the Jamf Security Cloud is a platform that makes these products possible because it's designed specifically to deliver advanced inline network services. Now, this next diagram shows an overview of the technical architecture of the Jamf Security Cloud. As you can see, the platform actually consists of two main separate architectures, the edge and the core, which are in turn composed of many smaller, separate components and capabilities. One key principle that runs through the entire platform is that this is all cloud-native, multi-tenant SaaS. This means that every customer uses the same single platform and benefits from the full power of the cloud. Now, if we look at the elements in more detail and starting with the edge, the purpose of the Jamf Edge is to get our network services as close as possible to end users to ensure latency is as low as possible. To this end, the Edge is primarily formed from a network of multi-tenant data centers we run around the world. The Edge is the globally distributed part of the platform. It's from this global network of data centers that we deliver our fast inline network services. The inline network services we deliver include Proxy and DNS, which form the basis of our threat defense and data policy products, and Packet Tunnel, which forms the basis of ZTNA. Another really cool aspect of our Edge is that we run a mesh network connecting all of our data centers together. This private mesh network forms the routing backbone of our ZTNA product and allows us to selectively route end-user traffic between different data centers to provide optimal connectivity to enterprise apps wherever they're hosted. Now, the last component called out in the Edge is the end-user app, which is installed on end-user devices to enroll them onto the service. Now, whilst the end-user app doesn't run in the cloud, it can still be thought of as a natural extension to the Edge, as we use it to apply specific aspects of routing and filtering policy. Okay, so that was the Edge. Now let's move down to the core. Like the Edge, the core also runs in the cloud, but unlike the Edge, it doesn't handle inline network traffic. Instead, in the core, we perform a broad range of centralized responsibilities vital to the operation of the overall platform. It includes over 50 different specialized microservices backed by various data stores, including our terabyte scale data warehouse. The admin console that our customers use to configure, manage, and support report on their deployment also runs in core. And then finally in core, we have our ecosystem integrations, which include our enterprise connectors, our APIs and feeds, which among other use cases support our seamless integration with the broader Jamf platform. Now, we can bring the architecture to life by overlaying 5 of the most common high-level use cases. In this first simple use case, we show an end user using Jamf Threat Defense, who in this example has been provisioned with a proxy configuration that causes the device to route web requests via our proxies running in the Jamf Edge. The proxy processes the traffic by calling out to separate filtering, classification, and policy engines, which are also running co-located in the Edge. And the results from the policy engine informs Proxy how to handle each connection and ultimately whether to block or allow the activity. This all happens in real time, completely decoupled from core and with less than 10 milliseconds incremental latency, and provides the end user with benefits such as our zero-day phishing protection. Right, let's move on to the second use case. And here we show how the platform processes updates to customer policy, such as changes to network security policy made by the customer admin. So the admin opens our web console, Radar, and uses the policy configuration page to make the necessary change. The console performs a CRUD operation against a policy microservice running in core, which first saves the policy update in our policy database before then publishing the update to every separate edge location via a distributed message broker. In the edge, the new policy update is made available to the policy engine via a high-performance key value lookup store. Now, this third use case shows a DNS deployment. This shares many similarities with the proxy deployment, but works on the DNS layer. So again, this end user may have been provisioned with the Jamf Threat Defense product. Now, again, the end user device is connected to the closest edge location, but this time only their DNS traffic is vectored to the DNS resolvers running in our edge. Similar to the proxy use case, we apply filtering, classification, and policy in real time, which ultimately determines which internet activity is allowed and which is blocked. But because it's a DNS deployment, only DNS traffic is routed via the Jamf Security Cloud. The actual content traffic, which is illustrated by that dotted line, will route directly to the relevant internet resource. Now, this fourth use case shows our ZTNA product in action. ZTNA is all about providing fast, seamless access to private enterprise resources whilst adhering to the principles of zero trust security. With this deployment mode, only device intended for the enterprise apps will be routed to the Jamf edge. At the point of ingress, the platform applies real-time ZTNA policy before then routing the traffic over our global mesh network to the customer's own data center, thus providing access to the protected enterprise apps. And with the final high-level use case to call out here, this shows the principles behind our dynamic risk-based policy. Risk-based policy is a key part of the ZTNA product and allows customers to define dynamic rules which stop risky or compromised devices from accessing corporate resources. The risk posture assessment is performed in the microservices core by collecting and processing multi-layer signal received from across the platform. Once the risk postures have been calculated, they are then published to the distributed edge using the same distributed message broker we use for publishing policy updates. Once on the edge, the policy engine factors device risk into real-time policy decisions, such as whether access to a given enterprise app should be allowed or not. Now, whilst there are other important use cases, the 5 we've been through are some of the most important, and hopefully they'll have given you a good understanding of the main features of the platform. Now, next, we're going to look at part of the architecture in more detail, starting with the software architecture of the edge. Right, so here we go. It's got a full-on diagram, and it shows the software architecture we use in each and every one of our edge data centers. The diagram shows how the architecture splits into 5 different layers. The top 2 layers host the custom microservices we run in the edge. The bottom 3 layers cover our modern DevOps stack. Now, in terms of the top 2 layers, you can see one of the most important architectural patterns which we use, which is the split of services between the data plane at the top and the control plane just under it. The data plane, which, as I said, is in the top tier of the diagram, is where we run the services responsible for directly handling end user traffic. This includes our fast layer 4 and 7 tunneling proxies, our advanced DNS resolvers covering both regular DNS and DNS over HTTPS, and finally our custom WireGuard-based VPN router, which we use for ZTNA. The control plane, which is the second layer in the diagram, is where we run the services which perform the business logic required by the data plane services. This includes fast policy evaluation, parallelized threat detection and classification engines, and also threat intelligence lookups. Keeping the business logic in the shared control plane, separate from the data plane, offers a couple of key advantages. Firstly, it keeps the services in the data plane very light and fast, which allows us to highly optimize them for processing network traffic. For instance, in ZTNA, we run an optimized UDP stack to achieve the best possible performance. Secondly, it enables the control plane services to operate as shared services. For instance, a single policy engine drives security policy across Proxy, DNS, and ZTNA. Not only does this reduce the amount of work required to build out features, it's great for us, but it also supports our unified management strategy as a single policy definition can drive policy across the full estate. The control plane connects back to the microservices core to sync policy, configuration, and reporting telemetry using a loosely coupled distributed message broker. This loose coupling between edge and core means the performance of the edge is always maximized and never adversely affected by load on the core or vice versa. Our language of choice for edge microservices is Golang, and we use fast optimized protocols such as gRPC to wire everything together. The bottom three layers of the diagram show our modern DevOps stack centered around Terraform and Kubernetes. A key benefit of Kubernetes is automated horizontal scaling, which is our principal strategy for handling increased load across both the data plane and the control plane. The DevOps stack also makes it easy for our dev teams to deploy the services they own using automated deployment pipelines. And we perform multiple rolling updates to the edge every sprint, enabling fast evolution of our platform. Now, we just looked at the software architecture within a single edge data center. Now we're going to see how multiple edge DCs come together to form our global edge network. So this diagram shows a zoomed out view of our global edge network. Each dot around the ring represents a separate edge data center located around the world. In each data center, we're running the full stack we went through on the previous slide, delivering our multi-tenant inline services of Proxy, DNS, and ZTNA. The global coverage provided by this network, combined with our optimized architecture, ensures latencies are kept low and bandwidth maximized. For Proxy and DNS, the data centers effectively operate in isolation. However, for ZTNA, the data centers join together to form a global mesh network, which we can use to selectively route protected end-user traffic to anywhere in the world. Now on the diagram, I've shown an example use case to show how this all works. Here, the remote employee, shown kind of bottom left, has been deployed with Jamf Threat Defense using Proxy, and then also with Jamf Private Access, which they're using to access two different enterprise apps. We can see how the employee has automatically connected to their closest edge location. The proxy provides network security for their general internet traffic, indicated by the orange arrows. Then in terms of the enterprise app access, the white arrows show the two different scenarios. For both scenarios, the device establishes a private WireGuard tunnel with the ingress DC. Then at the point of ingress, we apply real-time zero trust policy. And this is applied to every single packet, but we use a short 5-second policy cache to ensure this has virtually zero impact on throughput. Based on the policy outcome, we then selectively route the traffic over our global mesh network. This is true software-defined networking. For the protected SaaS app, we're using a routing policy of nearest egress, and this is optimal for globally hosted apps like Microsoft 365. In contrast, for the private enterprise app, we're routing the traffic over our mesh network to a Wandera edge DC on the other side of the world, which happens to be the customer's own private data center. In this way, we provide secure, optimal access to all the different internet resources required by the end user. Okay, So that was the kind of global edge network. Let's move on to the final part of the edge, which is the end user apps. As I said in the introduction, they can be thought of as a kind of natural extension to the edge. And we have separate apps for each of the enterprise platforms that we support, namely iOS and iPadOS, macOS, Windows, and Android. Now, as this slide shows, they have a consistent UX, which is tailored to the specific design idioms of each platform. Moving on to the software, each of these apps is developed as a native app. They all make use of low-level networking frameworks to deliver seamless integration with the Jamf Edge. In the case of the Apple platforms, we make extensive use of the network extension framework. We absolutely steer clear of using any private APIs or kernel extensions, allowing us to distribute our Apple apps via the standard public app store. The Android app is distributed via Google Play and the Windows app via SCCM or UEM. We extensively leverage device management, both for visibility and also to simplify our deployment, including enabling a number of advanced zero-touch deployment options, which are required for enterprise-scale deployments. Along with the platform-specific code, we also have a couple of libraries used across all 4 platforms, which are those boxes striped across the bottom, namely our identity integrations and also our advanced custom packet tunneling capability built around WireGuard, and which we use as the traffic vectoring technology for our ZTNA product. Okay, right, so far we've been talking about the edge. Now let's move on to the core. And here we go. So this diagram shows the software architecture of the microservices core. Now it should look familiar, as the core architecture has many similarities with our edge architecture. Now, the most important similarity being we use the same modern DevOps stack in both our core and edge data centers. So the bottom 3 layers of the diagram look the same as they did on the edge diagram, and they support the same critical capabilities, such as seamless horizontal scaling, robust multi-AZ operation, and our modern DevOps workflows. Now, the difference with the edge is in the top 2 layers. Remember, back with the edge, we were running an advanced data plane and control plane, but here with core, we run an application layer consisting of over 50 different microservices, which act as the management plane for the platform and cover functionality such as device provisioning and lifecycle, platform orchestration, policy management, threat intelligence management and distribution, threat workflow, and reporting and analytics. I'm sure there's more. Now, whilst many of the capabilities that run in the microservices core support the functionality of the edge, there are also important standalone features, so features that run entirely within core. So for instance, the App Insights feature, which provides detailed insight into the risks associated with the apps installed on end user devices, operates entirely in the core. In terms of the microservices running in the application layer, they're implemented using Java and our preferred Spring Boot framework, and are connected together using either our message broker or REST APIs. The microservices in the app layer are supported by a very capable data layer, which is the second layer in the diagram. This features a number of different databases, both SQL-based and NoSQL. Also, our terabyte-scale data warehouse Vertica, our stream processing platform, and a powerful Spark cluster used for training the machine learning models that we use both in core and then also distributed out across our edge. One of the most prominent services running in core is our admin console. I've shown a few screenshots showing some of the reports we offer. The console itself is a modern React-based web client. In terms of the reporting, this is all driven by our data warehouse and our stream processing platform. For instance, to drive the network activity reports that you can see here, we stream activity logs back from each of the inline services running our edge. We then utilize fast loading techniques to mean that we have a log to query time of less than 60 seconds from across our entire distributed architecture. This ensures that admins get near real-time visibility across their ZTNA, security, and data deployments. Another key aspect of functionality delivered from our core is our ecosystem integrations, where we offer a range of connectors, feeds, and APIs. Our UEM connector supports integration with device management solutions such as Jamf Pro. This is implemented as a horizontally scaled stateless microservice, which uses internal queues for job management. This architecture makes it highly scalable and equally robust. It also uses a modular adapter architecture to allow for flexible expansion. We also provide an IDP connector, which supports integration with Azure and Okta required for ZTNA. And finally, we provide a range of APIs and feeds to support a broad range of security ecosystem integrations. This includes our REST-based risk API, which allows external sources to set device risk and so drive ZTNA policy, and also our threat event stream and network event stream, commonly used to drive external SIM integrations, such as with Splunk. Right, we've arrived at the final detailed slide before the summary, and this one shows one of the key strengths of our platform. It shows how we use proprietary threat intelligence, machine learning, and multi-layer signal to deliver real-time visibility and risk posture for each and every device on our platform. So kind of starting at the left, we collect this rich multi-layer signal about every device from three main sources. The first source is our network edge, where the inline services stream network activity logs back to the management plane. These logs include enriched information such as threat detection events, app identity, and policy outcomes. The second source of signal are our native apps. Having a footprint on the device allows us to collect device metadata and perform client-side security checks, such as man-in-the-middle threat detection. The third and final source of signal are our extended sources, such as our close integration with Jamf Pro, which provides extended metadata about managed devices. We use the multi-layer signal to drive threat and risk modeling. We've developed a sophisticated stream-based architecture to process the inbound streams. Our state analysis engine uses our proprietary threat intelligence to detect further threats and vulnerabilities in device state. Together with the activity logs and threats from the network layer, these form a rich multi-dimensional model of every device. We apply the customer's security policy, including their customized risk settings, and based on this, generate a real-time risk score for every device. The resulting risk score supports numerous internal and external use cases. For example, device risk score is signaled to the edge to drive real-time contextual policy. Threat detection events are used to drive customer reporting and notifications. And the enriched traffic logs and events can be streamed to our external feeds to consumers like SIM and CASB. Okay, so that's it for today. I haven't been able to cover all of the great aspects of the Jamf Security Cloud, but we've certainly covered good ground. And hopefully, if nothing else, you'll remember the main takeaways up on the screen now. The Jamf Security Cloud is a modern cloud-native platform which uses a multi-tenant microservices architecture. We've talked about the two main parts of the platform being the edge and the core, how the edge is formed from a network of data centers we run around the world and where we deliver fast, advanced inline network services to our end users, and the core, which is the management plane for the platform, and how it features a broad range of advanced capabilities, including the multi-layer threat signal processing we just looked at, which drives our risk-based modeling. Okay, that's it for today. Thank you very much for listening, and I look forward to working through the Q&A.